you'll get, oh, there you go. I was going to say you get a message coming up. Okay, so I'm not going to delay the start. I'm going to pass you over straight away to Sally and Chris, who are leading the session. Thank you.
Thanks a lot, Sean, and thanks, Arian, as well. Good to see some familiar names here and some people from the first session, I think, as well, and some new names. My name's Sally Bamber, as you can see, and I work at the University of Chester, particularly in maths education. And I think I've been working with Chris for about 4 years now on these projects. Is it, Chris? Something like that?
Yeah, I think so, yeah.
Coming up to that, isn't it? Like every time has kind of taken on a different scale in the last 2 years anyway, or something like that. Great, thanks. And you are, of course.
Oh, I'm Chris Hemmy. I forgot my introductions. I'm head of maths at Connah Quay, and like Sally said, I think we've been doing it for about 4 years in school. So, you know, Sally worked with the previous head of maths as well. So she's been in and out for a while.
Yeah, great. Thanks, Chris. So we've had the first workshop, and you have the link, I think, that Sean sent, and you can catch up on that at any time. But what we were trying to do in the first workshop was think about algebraic thinking within number, and then think about how those foundations of presenting concepts in number in a particular way can help support the structure of algebra once people start to symbolize and bring in letters to represent the variables and so on. So we're thinking about algebraic thinking that might not necessarily look like the traditional kind of algebraic tasks that you might see, but certainly are using the sorts of ideas that we want to stimulate in terms of algebra. So the second session, as I will share now, hopefully, you can see we're going to start thinking about connections and structure in algebraic expressions, which is a huge thing to think about. But what we're hoping to do in this session is just perhaps focus in on linear expressions and just think about those today. And the idea there is thinking about connections and structure within linear expressions deeply and well, so that when things move on to other applications of algebra, or perhaps put in linear thinking in other contexts, perhaps into straight line graphs or into sequences, this has been done well so that those ideas can be built upon in those other areas. And then, of course, as you'd imagine, the linear work done in linear expressions and linear equations can then be used to stimulate thinking in quadratics and think about what ideas can be used that are the same and which ones are different, and then hopefully supporting a wider understanding, a broader understanding. So building on what we did last time, we started with a maths problem to give people some chance to think about some of the maths. Hang on a sec. Where's my maths problem gone? There it is. So a little challenge for you. I've forgotten what my rectangle looks like, but I remember that it has a perimeter of 24 and has the biggest area that I could make with this perimeter. So what could my rectangle be? So I'm going to give you a second to, not a second, I'm going to give you a minute to have a look at that, have a go at that. And then we'll have a think about some of the things people have done to solve that problem. Okay, folks, it doesn't really matter if you haven't finished this problem, because I'm going to be interested in how you started it more than anything. If you want to pop something into the chat about what you've done with that problem or what you've come out with that problem, absolutely brilliant. And if anybody would be happy to switch their cameras on and just talk to us about how they approach that problem, that would be fabulous too. Otherwise, I can pick on Chris and ask Chris to share his.
Mute button's always in a different place on every type of
I know, yeah. Okay, do we have anything in the chat? Let's have a look. Okay, Chris, did you have a go at that problem?
Yeah, just press something else now, sorry. Just thinking about drawing some rectangles with a perimeter of 24.
Okay, brilliant. So you took some particular examples and started with some particular examples. Okay, did you just kind of draw them and then find the area afterwards, or have you not got around to finding the area yet?
Yeah, no, found the area as I went. So look for pairs of numbers that sum to 12.
Okay, brilliant. So 12 is part of this problem for you now as well, which is great. Okay, fantastic. I don't know if people can see my mini whiteboard, but if we're trying to think about what's going on here, if we've got 24, then we know we're going to have 12, but we're going to take some off it to be able to give some here. So if I give 2 to this, then this becomes 10, and then I've used all of my 24. So I've got a particular example there, and I can see that the area of that would be 20 from what I've got going on here. Chris, what was one of the other examples you did?
I went for 8 and 4.
8 and 4, okay, fantastic. So we've got 8 and 4 still following that principle of 12, and we could think about what that might be all about. And then you've got an area there of 32. This is usually where I get my calculations wrong. And we can see we could start to think about this systematically. We've got a width of 2, a width of 4, so we might squeeze in the middle there with a width of 3. And think about what would go there. Well, if we need to make these add up to 12, so 12 and 12 will give me 24, then I'm probably going to use 12 subtract 3 at that point. And then we can start to see that that would be 9. So far, this is the biggest area that I've got. Okay, fab. Thanks, Chris, for being put on the spot there. Has anybody popped anything into the chat? Any solutions in the chat or anything? Has anybody done any other examples? And they would be willing to pop that into the chat.
I noticed it's divisible by 4. So it's actually a square, isn't it? So you could get 6 and 6 on either side.
Okay, brilliant. Thanks, Sam. So you found an example that seems to be the biggest, and you've got 6, 6, 6, and then you've got your 36 as the area. And that is, as Sam said, that is the optimum area because it's a square, which is fantastic. So it's following my rule. Now, what we were hoping to do here was start to think about what the role of algebra might be in a problem like this, and start to think about, is there actually a variable working within this particular problem? So at the moment, it's quite hard to see everything that's going on there. They're my rough scribbles that were going on there. But if we think about how Chris was perhaps working systematically here, first of all, he had the 12, which is a really nice generalization. That if we're going to have a perimeter of 24, we know we're going to have 12 to go all the way from here to here. Fantastic. So if I've got 12 and I'm changing this width, then this might be something that I would give a label to because I'm varying it. And this would have a corresponding variation because I've varied this. So if I change this to 5, then this would go down to 7. If I change this to 4, then this will go up to 8. So we've got that lovely relationship going on there where my area is always going to be 12 minus x multiplied by x. So there's some lovely generalizations going on there. And if we were to draw the graph of that, we'd see that Sam is exactly right, that the highest point would be when x equals 6. So he solved that absolutely beautifully. But what I'm suggesting here is that what's gone on is some particular examples have perhaps given a little bit of insight then into some general examples. And that's something that's true very, very often in mathematics, that if we go from something that's very specific, if we specify, and then we move on to something that we want to generalize, that is a really good thing to do, because that's something that is involved in being mathematical and being a mathematical thinker. So thanks, Chris and Sam, for those illustrations. If we think what the role of the variable is in this case, we could solve that problem really successfully, which I imagine Sam and Chris did, without actually bringing in any algebra. But what they're actually doing whilst they're solving those specific problems is starting to expose the structure of the problem. So if we do get to the point where we perhaps want to use expressions like the 12 minus x as an expression to represent the length, if somebody's had the experience of seeing that length go down as the width goes up, then they've got some insight into what we call the structure. So they're able to make connections between the algebra and between the specific examples that they've been doing in the number. So I chose this example so we could perhaps start to think about what do we actually mean when we're talking about structure. So just recapping on, sorry, this isn't moving forwards, there we go. Just recapping on some of the things we talked about last time and my possible obsession with sweets. We've got the idea of using sweets now is going to be something that's going to model a discrete countable object that can be varied. So it's going to be a variable that's a discrete countable object. So what I'm going to be doing is, as we did last time, we looked at some of these specific examples using these Skittles diagrams, where we're able to connect an image like this with an expression like this. 10 add 4 times 5. So if we go back to the image, we can start to see how the structure of that picture and the structure of that expression can become connected. We can see the 10 and we can see the 4 multiplied by 5. And therefore we're able to see that we've got 10 plus 4 times 5. And then we could do something similarly like this, and we could start to perhaps think about why it's really important that we multiply those two terms together to have 2 times 7 worked out and 4 times 4 worked out before we add them together. And we can use that image to perhaps expose some of the structure of why we would want to do that if we wanted to know how many Skittles were on the sheet, how many sweets were on the sheet. And then we can start to look at some images like this that perhaps are using what I called last time, that kind of really important, significant image where we're using the array. So we can start to think about expressions that might match this, like this one or this one. And we can make sense of that image as 3 rows of 3 add 7, or we could make sense of that as 2 little arrays within the big array, and we can think about 3 times 3 and 3 times 7. And the important thing is that those things can start to be thought of as equivalent representations, but not identical in the sense of the way we think about that in everyday life. They look different. And when we go back to that image, we can start to see how one tells a slightly different interpretation, reasoned slightly differently than the other. So we could think about how many red Skittles we've got first, and then how many green Skittles we've got, and add them together, in which case that expression would tell the story. Or we could think about how many we've got in one row, where we've got 3 add 7 in one row, we've got 10 in one row, and then we've got 3 rows. So perhaps that expression would tell that story. And in both cases, that image is helping us to have some insight into the structure, what this means, how it's built, how all of those different numbers and symbols are connected, and what it's representing. And in all of those 3 examples, what we're not particularly bothered about is how many sweets are on the screen. We're not particularly bothered about that because it's the insight into the expressions that we're actually concerned with at the moment. And then terminating on the idea, oh, look, they're both representing 30 sweets. That's easy. That's the easy bit that follows as a kind of natural progression from understanding the structure of the problem in the first place. So we're going to carry on with this idea now, but then we're going to move into some idea of generality. So I've used a packet of sweets again, as you can see here. And this is something that I use as perhaps a very, very first way in to bridge specific examples into more general examples. Now, this isn't actually acting like a variable at the moment because there is a fixed number of sweets in most packets of sweets. There's usually the manufacturers have exactly the same number, or we can assume they can. So it's not acting particularly like a variable at the moment, but it's really useful in that most young people realize that there's a number of sweets in a packet. And they also perhaps did something like this. It's not small enough for them to know exactly what it is. They're not going to shout 5 out like they would if I was using a packet of smaller sweets. But they also appreciate that there is something discrete and countable inside it that they could guess. So they could perhaps suggest there's 40 sweets or 30 sweets or 20 sweets inside the packet. So when I ask them how many sweets, we'll get some guesses, but then hopefully we'll also get this idea of, I don't know. So then we can start to think about how we might represent that not knowing. And we can think about saying statements like the number of sweets in 3 packets add 12. Or we could say statements like 3 times the number of sweets in 1 packet plus 4. And we can design our images to help expose the structure of the problem that we want to draw the students' attention to, the structure of the algebra that we want to draw the students' attention to. So similar sort of story for this, we could say that we've got 4 times the number of sweets in one packet, add 20, or we could think about the number of sweets in one packet, add 5, multiplied by 4, and we could start to see those 4 equivalent groups going around the screen. Similarly with that, and then if I wanted to, I could start to think about, well, what would happen if I ate 5 from each packet? So this time we were talking about the number of sweets in the packet, subtract 5, multiplied by 3, or an expression to represent the whole thing might be that I've got 3 times the number of sweets in the packet, but I've eaten 15. So we would represent that obviously as subtract 15. So bringing about another idea here, this idea is that we would use a cup, and hopefully an opaque cup that the students can't see through. And we'd use a cup like this, because what can happen now is when I'm putting sweets inside a cup like this, it can start to be a variable. It's no longer a fixed number of sweets like it was with the Skittles image. It's something that I can vary. So what I'm able to do is start to think about how might I build about an image or a picture or an actual physical context using the cups and using a desk or using a visualizer where I could represent that particular expression. So what I would usually be doing for 3 brackets n add 4 is starting to think about, okay, well, we've got 3 packets, 3 cups of sweets. I'd have 4 individual sweets going on each time. And then I could start to think about how we might represent that. And you'll see some of the diagrams of this in a moment, because it's a little bit awkward doing it with my computer camera, but I'll show you some of those images in a second. But then we can start to think about what might happen then when we start to think about an equivalent expression. So we can make sense of that, the sweets in the cup and the single sweets as 3 times the number of sweets plus 4. So 3 sections where each section is a cup with some sweets in plus 4, or we can think about the whole thing as 3 times the number of sweets, so the cups bit, and then the add 12. And then we could do it for this, and then we could do it for this. So different expressions we can do that for. And in each case, we're trying to get students to appreciate that we've got equivalent representations of exactly the same algebraic expression. So we've got equivalent representations there where they're known to be equivalent. So rather than us thinking, okay, we're expanding brackets here or we're factorizing brackets, we can start to use this idea of actually we've got 2 different representations of the same expression. And in different contexts, each of them are useful. So later on, the first one, the 3n add 4, 3 brackets n add 4, is going to be useful to represent perhaps the dimensions of a rectangle, whereas the one 3n add 12 is going to be useful to represent the area of a rectangle. So to bring students to that point where they're able to actually make sense of equivalent expressions is hopefully going to equip them for being able to solve some equations. Hang on, screen's not moving forward again. Okay, so what have I done here? So this is an expression 3n add 7 equal to 12. So you recognize that straight away as a linear equation. But what we're hoping to do is try and encourage a more structural insight where students are able to see that we've got an expression on the left-hand side that's equivalent to an expression on the right-hand side. And often, particularly in the initial stages, the expression on the right-hand side is something that's a number, and they might just see this as an output. And that idea can sometimes be problematic, as you probably know. So the reason it's problematic is that they think that every linear equation is going to take this structure of an expression equals 22, equals a number. And so if they think that that's the case, they're not necessarily going to be equipped with the sorts of thinking in algebra that will help them to solve other equations or equations that aren't presented to them in that way, or even start to think about how can we use this idea of expression equals expression in quadratic or all sorts of different other contexts for equations that they'll meet later. But back to the sweets in the cup. So what we can do here is start to think about having things that need to somehow balance or somehow be equivalent. Now you've probably seen, and we'll have a look at some pictures of those in a moment, where this idea of solving equations is introduced actually using a balanced scale. But that's something that can be problematic, particularly when you're trying to make things believable, because the cups have a weight and the thing's not necessarily going to balance. So I think it's easier to actually just use this made up context where you have on one sheet of paper or one side of the desk, you have 3 cups with equal numbers of sweets in each cup, add 7 sweets, and that's the equivalent number of sweets to the 22 that you can see in the right-hand side. So when we start to ask students to think about how would we know how many sweets are in one cup, they can start to do that quite informally, just using that image that you can see there using the cups. And sometimes with all sorts of different groups of students, they've been able to shout out the answer. They've been able to see the answer straight away from what we've done here, because they're starting to do things like thinking about within the 22, I can see a 7 and I can see a 15. So they start to think about perhaps those 7 can just be compared to each other, or as we often think about it, taken away. We can remove them from the context on the left-hand side and on the right-hand side. And then as soon as they get to that point, they're shouting 5 out. 5's popped into their heads, and they're able to tell you that there are 5 sweets in each cup. And this can sometimes be with students who, when I'm working with students who perhaps got a lot of anxiety in relation to algebra, they can see problems like this and they can find solutions to problems like this. But that doesn't necessarily mean that they can follow that particular discipline that you can see with the 3n equals 15 and the n equals 5. Just because they can see that there are 5 sweets in the cup doesn't mean that they're therefore able to translate that into the algebraic context and the symbolic context. So what this work is about trying to connect those representations so that students can make connections between both of them, between the context and with the discipline that you can see with the algebraic equations. So we'll talk more next time in the next workshop about equations, but I'll just, So what I meant to say here is that we've moved on from thinking about equivalence of expressions to now thinking about equating, saying that one expression is equal to another. And therefore we need to find the value of n, which will make that true. Because if I chose another value of n, this wouldn't be true. So in an equation, that relationship is either going to be true or it's not, depending on which value of n we've got. But when we go back to equivalent expressions, like we have here, then those 2 expressions are going to be equivalent for any number that I choose to represent n. So we're talking about different notions of equivalence and equality going on here. And that can be quite complicated. It's probably something you've thought about already in the way that you structure your teaching. And what we're hoping to do through using these sorts of representations is help students draw attention to these ideas as well. So an example of that within an equation, we can see in this problem here, using these sweets in the cup, we can start to see, oh, I've got 2 groups there. So perhaps I can start to split this up into saying, well, if 2 groups of n add 7 is equal to 30, then the number of sweets in one cup add 7 must be equal to 15. And therefore, the number of the sweets in the cup will be equal to 8. Or we can approach that a different way, and we can start to say, okay, well, if I understand that 2 times brackets n add 7 is equivalent to 2n add 14, then we've got 2 different ways of solving exactly the same equation. And the route to get to the solution is different, but the answer is exactly the same. There's n is equal to 8 in both of those versions. The other thing we'll talk about a little bit more next time is the power of this model of expression has to be equal to expression when we start to do these sorts of equations where the unknown is on both sides, which traditionally, if you look at textbooks that have been published, say 15 years ago, you'd see this in the harder section, seemingly harder. But I'm not sure if it is harder when we have a way of knowing it, as you can see in these expressions here. So we've got the idea that we can find that something is equal or it's not. If I put n equals 10 into that equation at the top, it's no longer equal. But if I was to have, go back to those expressions we had a minute ago, the 2 equivalent linear expressions, if I put n equals 10 into any of those, each of the pairs will be equal. So we're trying to get students to think about, or we can have equivalent representations But then we need to think really carefully in mathematics about when we're trying to say whether two expressions are equal or they're not. Okay, so I'm just going to stop there for a second, and we will, screen sharing has stopped as the shared window is closed. That's good. I'm glad that's what I wanted. So if we just pause there for a second, and let's just have a think about how we might represent a particular expression using the sorts of sweets in a cup images. So if I was to say that we want to think about what might be equivalent to 3 brackets n add 2, if you could draw a picture for that using the sweets in the cup model, what might that image look like? Okay, is anybody happy to switch their cameras on and just flash their piece of paper up to the screen for us? Or I was going to say, if you're super quick, you might be able to photograph it and pop it in, but that might take a little bit of time. Anybody able to share that with us? Thanks, Sam. Okay, brilliant, excellent, fab. So we've got 3 cups, which are neater than mine when I hand draw them. And within those 3 cups, let's move that over, try and be neater, 3 brackets n at 2. We've got 3 cups, and then we've got 2 dots to represent each sweet. So of course these aren't sweets, these are cups where they've got an equivalent number in them. And then if we think about how we might make sense of that, we can start to interrogate the structure by asking questions that allow students not to think about, okay, today we're expanding brackets and tomorrow we're doing substitution. We can pause and we can ask questions that expose that structure by asking for students to evaluate these right now. So using both of those expressions, if I ask students the question, how many sweets do I have altogether if there are 10 in each cup? It's the same as asking, what's the value of this expression when n equals 10? Well, it's the same to me, but it might not be the same to your students unless they're given the opportunity to connect these 2 representations. So if I wanted them to make sense of the structure within this, I'd have to start asking them questions that really reveal the structure. So I can start to say things like, okay, I can't remember how many sweets were in each cup, but I can remember that I've got 33 sweets altogether. And then the students can start to think about, oh, okay, well, if there's 33 sweets altogether, there must be 11 in each group. Or they might think, okay, if there's 33 sweets altogether, 6 of them are already taken for these 6 individual ones, so there must be 27 altogether in each cup. But they can informally start to make sense of those problems where they're actually just getting some insight into the structure so that when we do tackle the algebra in a more traditional or more formal way, they've got some experiences that the teacher can draw on. Okay, I'm just going to stop, pause for breath there and invite any questions. I don't know if we've had any in the chat whilst I've been talking. No, haven't got any. So has anybody got any questions about the sweets in the cup model? I know some of you have seen this before from other work that we've started before lockdown and also from being on courses at Chester. Anybody got any comments or any questions? Has anybody used a similar model to this? Now, I'm obsessed with food, so I do use food as often as possible in the maths context. And I also think it's something that's quite unifying because as long as you're not choosing insensitive foods, then you've got something that everybody understands and everybody can connect with. But equally, I think it's really good to use things like the number of pens in a pot or the number of lollipop sticks in an envelope. The most important thing is that they're introduced to these ideas with a discrete countable variable. So they're not having to make sense of something continuous and worry about decimals and worry about the numerical aspects of this. Numerical aspects are not going to put too much demand on them, but they can think of a discrete countable variable that they don't know. And then we can start to ask some questions that exposes them sort of interrogating that understanding and interrogating some of those things. Okay, so I'm going to press on and I'm going to be as quick as I can. I'm just going to introduce you to where that goes, but then hand over to Chris as soon as possible. Because as I've just emphasised, this is a discrete countable variable. I haven't got time to talk to you about fire of doom, but it's a really brilliant problem So hopefully you'll have a chance to have a go at that if you want to have a look at it, if you haven't seen it already. Anyone who's been on the PGCE at Chester has been forced to do that at some point, whether it embarrassed them or not. But what I want to do is just move on to when a variable might actually be continuous. Now, we've chosen perimeter as a context in the projects that I've done because it's something that's realizable. It's something that the students can experience, but also it means that they're actually developing their insight into an aspect of geometry and measure at the same time as they're developing their algebraic insight. So I use this word realizable quite a lot, and if anyone's familiar with the RME projects that MMU are promoting and have been working on for decades, this word realizable is really important because it means the context's not realistic, but it actually gives them a context that students can realize. So I hope that the sweets in the cup help students realize some connections between algebraic expressions and the number of sweets that actually might be representing that variable. I hope they can realize that, even though it's not a realistic context. We can all get through life quite easily without setting up problems with sweets in a cup. But when we come to then thinking about moving this into a continuous variable, length is really, really handy. So if n represents the length of the side of a regular pentagon, when we've introduced this to students, they've struggled a little bit with understanding what that means. So the classes that I've been working with, we've used art straws to actually construct the perimeter using the art straw. And then we've started to think about what would the perimeter be if n equals 10. Now, if my art straws look like they're about 40 centimeters long, but perhaps not going to help. So sometimes I work with the kind of experiences and think, well, I'll make these sticks now, I'll break all the art straws up so they look like they're about 10 centimeters and use that as my frame of reference. Then we can start to think about, well, I'll make them a little bit smaller now. What would my perimeter be if n equals 7? What would my perimeter be if n equals 20 or 13 or 0.5, even a little teeny tiny perimeter going on there. But the idea is that students are starting to think that this is actually representing a variable. And what happens on the table or under the visualizer while we're modeling this is the perimeter is getting smaller and the perimeter is getting bigger. And so they're appreciating what we mean by this n being a variable. And we don't know what it is unless we assign a value to it or we're given some other information that helps us find it. So I won't go on about this too much because we've got some really interesting stuff that Chris is going to share with you now, which extends this idea of a length being used to represent the n. But what I will say is that students once again can start to get into the structure by not doing a separate lesson on collecting like terms or expanding brackets and so on, by doing those things together, so that they're simplifying the expressions for perimeters at the same time as they're interrogating the structure by thinking about what it would represent if it was assigned a particular number. So we've got these questions that you can see popping up on the screen here, and students can start to think about those shapes when they're investigating those problems. So then we can then move this on to something that's perhaps a little bit more recognizable, because what we're doing now is actually using the n add 3, where those little green squares are representing the ones. And then we can think about problems that you might solve with that, where there actually might be sometimes at the end of a challenge on a traditional worksheet on expanding single brackets. But what we're trying to do here is actually not have a hierarchy there where expanding brackets or factorizing equations, one is harder than the other. We're trying to bring about the equivalent expressions by having the image is fixed. So the pentagon with the side length of n plus 7 is fixed there, and then the expressions can be represented in 2 different ways. And we can ask all sorts of questions around that, and then we can get students to apply this to problems that might not automatically have those sticks available. They can draw the sticks on top of this to help them make some sort of meaning out of the work that they're doing. And then you can probably recognize that as a GCSE question, and they can draw the 2 sticks either side for AB and AC to represent the 2 X's that are going on there. All sorts of different things we can do then. We can take these images and start to think about, I want an expression for the perimeter, or they might have something like this that's representing a rectangle and they want to find what n is, because they would know that, or hopefully would know that the opposite lengths are equivalent. So in this one, I could ask them a question where they're trying to find an equivalent expression. So instead of those 4 different expressions added together, we could simplify this and find out that we've actually got, what have we got there? 10n add 10. Whereas this one, we could start to think about equating those 2 lengths and saying that I want to know which one value of n will enable me to have 3n add 12 as the same length as 5n. So we've got those different, slightly different applications going on there that we can use. But hopefully, even in the short time that we've got here, you can see that transition there from a discrete countable variable into a continuous variable, which will hopefully help people with the stage that Chris is going to share with us in a sec. Has anybody got any questions about the perimeters before we move on? Okay, fab, that's great. Thanks, Chris. I'll hand over to you if that's okay.
Yeah, no worries. I'm just going to talk a little bit about where it goes to with Algebra Tiles. I haven't used the stuff Sally's just shared. I've used as PowerPoints, but not physically got the straws and the cups and stuff. But I think with some of the young years, that's the next step. Is getting that sort of stuff in. I'm going to see if I can do this. This one, share. So this is the sort of introduction to Algebra Tiles. After they've done the work that Sally's done, we sort of introduce what an Algebra Tile is, all positive at the moment. And is that going to change? Yeah, slides 3 down to 14 we give as a matching activity. I don't really tell the children more than that at the start. Just sort of give them out and see what they make of it. I've shared this slide with them beforehand to sort of just so they know it's an X and it's a 1, and then just let them go for it. Give them a few minutes to struggle, see what they come up with. Lots of them sort of figure it out in the end because it's got 6 rows and there's not a real maybe need to throw one in where there's 2 sets of 6, but so a lot of them get it, and then we just will sort of work through. So we sort of, is this gonna work? So it goes through, and once they've paired them up, I then ask them to sort of describe to me what that is. So using what they've just done, how would they describe that? And we end up with, the 4 rows of 6, and we go through why it's 4 rows of 6, because it's 1x, sorry, 4 rows of x plus 6, 1x plus 6 ones, and it's repeated 4 times. There's 4 of them, and then we run through the answers with their sorts of pairs, and it just gets them thinking about the structure. So it has to be a rectangle. It follows on a little bit as well from the last thing we had with the 48 with the Dean's blocks, and sort of going from that fixed set of 10 into a unknown. So if that was with the Dean's blocks, that would be obviously 9 times 12, but we go through it to sort of show that it can't be measured. And the Algebra Tiles, we use these blue Algebra Tiles on card cut out. Like I think I mentioned it last time, there was one lad when Sally came in, was determined to figure out what the length of the X was, and spent about 5 minutes with his ruler. He had his phone out at one point taking a photo so he could zoom in to the ruler to try and figure out what the length was. So we just work out, and then there's obviously some different ones, so it's slightly different. So there's no sort of building up. Traditionally, I probably would have done just all single X's to start with, expanding a bracket. So we're doing a lesson on expanding, a lesson on factorizing, just keeping it with just 1x. But this just goes into it. So if they understand what these are, then why shouldn't they just understand what that is? It's just extending it that extra little bit. The language is obviously very important. We've talked about this before, but using that 5 rows of 3x, 6 rows of 2x plus 1. And so there's no difference really between having a single x or in this case 2x's. The the other way I've seen this done is with a whiteboard, so not using it as a matchup, but if I just flick back to the start, draw that for me, or put the tiles out and make that for me. So rather than it being a matchup, it's we go through that first slide first and then make it, draw it. So they do that, and then same again, and then that what's that one then? I've made it this time. You tell me what it is. So you know, lots of use of mini whiteboards, lots of use of the tiles, physical tiles on the desks. And then that one is just thrown in just to see if they sort of rewrite it the other way around and get that structure in with the different. So understanding what each part of the sentence is. And it works quite nicely. Lots of them still want to write 5 rows of X and turn it round, but it's that then discussion, isn't it, of each part of the word has a particular meaning for the array. The other thing we do with these ones is sort of throw that in. Let's go back to one of these. So if X is 4, what's the area of that array? So sort of revisits the area topic. It gets them doing a bit of substitution. So it's not just an introduction anymore. There's a bit of substitution straight away. Build that up if X is 1. So similar to what Sally's just said with the perimeter problems. And then sort of put some areas in. If the area is 60, 63, what's the value of X? And look at the different ways in which learners solve it, going sort of solving equations without them having to sort of see the equation and work backwards and forwards. So, you know, this is at least a lesson, maybe a couple of lessons, just building up with that language and that those skills of substitution and figuring things out. We then put this one in. So this was a challenge for sort of those. So just getting them interrogating the structure of. So I can't remember, forgotten what the array I built. So they're going to have to make one. This is where the tiles come into use. I can only remember that when X is 3, the area is 48. What was the array? And getting them to do this is a nice open-ended problem because there's obviously more than one solution. Getting them to think about how they do it. So is this the sort of have a little think about how you would do this? What would you expect to see if you did this in the classroom? And how would you go about solving it? If we just leave it for a couple of minutes, see what different solutions you come up with. So. I don't really know what I'm doing with Zoom. Can I see chat and stuff while I've got my screen shared now?
I'll have a look at the chat, Chris. Thanks.
Just if anyone's got any questions or while we're doing this, just put them in. But what would this look like for you? If you had to solve this, what would you do first? There's nothing there. What sort of when one of my classes did it, what a few of them just did was just pick up a load of X's and start to build along until they got there. So they had one big, massive, long strip length of the desk that was 16 X's, one row of 16 X's. Okay, brilliant. Well done. So now what? Some people did it down, so they had 16 rows of 1X. So yeah, like that. So for sort of those, I then said, well, you've got to start using some ones. What would happen? A few of them started to notice that a few of them started to swap out an X for 3 ones and see where that got them. But it just promoted quite a nice discussion. It's quite a nice open challenge that everyone can get one. It's one of those, isn't it, where, you know, as long as everyone can get one, the sort of brighter ones can run with it and come up with their explanation and things as to why.
I think that's really nice, that kind of big long one row. So one row of 48 being expressed, you know, with the X's within there as well. But that was then like a stepping stone into having 2 rows or 4 rows or three rows. So even though they started with a really simplistic starting point, once they'd done that, they were able to see how they could actually build on it and change it. Yeah.
So it was quite nice, and a few of them just look at it at first, don't they, and sort of go, nothing. I've got nothing. And then so it's just pulling out the X's and saying, okay, so that's 3. So you need to make me a rectangle, make me an array. So it's 48, and you know they get there in the end. But it's a really nice lead-in lesson. I'll just sort of jump back to your PowerPoint, Sally, where.
Yeah, we've got far too much on these slides. We're not going to talk you through 20 slides now, but we just left them all there so that you can have a look when Sian sends the PowerPoint out, and you can start to look at how some of the ideas might develop. Yeah, sorry, Chris, I was just explaining why there's so much there.
There's just them goes up onto this. So this is sort of the start of the next lesson. So you're sort of making it a little bit more structured, so they can make their diagram. So, you know, you get different types of one. You've got people that have got the same one. So it's just building up. And then this goes into using the factorized version with the brackets of expressions. So you're coming away a little bit from rows of. I tell mine that the brackets, we draw the brackets instead of writing the words rows of. And that's what the brackets mean. And they get they seem to get that okay, I think. I write it, so then from now on, when I start writing it, I will write the brackets but will say rows of when I write the bracket. So I would write this expression as 2 bracket 2x plus 6, but I would verbally say 2 rows of 2x plus 6 and then close the bracket off. The best solution I've had for this so far, this question is, it's more square. And for sort of some of the younger ones understanding that's what they need, isn't it? They need that sort of that version. So it's more square. The more square you can make it, the better. Some of them then get to say, well, the number outside, the number of rows is the biggest it can be, which obviously does nicely onto when you factorize into the highest common factor. And then there's a few sort of like that that fit in. And then, you know, a lot of what I've taken from the work with Sally is using questions like convince me and why, show me why. Here's the answer, show me why. So it's not a case of they're puzzling to get to the answer and there's a goal of, oh, brilliant, I've done it. Okay, why? How did you get that? I don't know. That I just sort of got it. You've already given them the solution. They've got to work out the steps to go. And then you're bringing in, you know, some sort of the other language there with equivalent expressions and factorizing and things like that. So it goes quite nicely. And there's a slide that's missing that I've used. It's got a few. They have to factorize expressions, and there's one that doesn't factorize. And I'll never forget the one girl. The first time I did it, one girl was determined that it would factorize. So she wrote 1 bracket. I think it's 11x plus 15. 1 bracket 11x plus 15, and told me she'd made an array. It's 1 strip, and she's factorized it. And and I'm sure if you asked her to this day, she'd probably still say the same. But it just builds up nicely into that form of factorising and expanding brackets without having those lessons of 50 questions with expand this, factorise this.
Chris, that was really interesting with your class. What I didn't say at the start, which I should have, is the project work that I've done a lot of with Chris is about raising attainment in GCSE. But what we're now working on is adapting these things to the whole of Key Stage 3, you know, building the algebra thinking across the whole school. I was just going to say, can you share that slide 50 something? But don't worry, I'll do it. But there was a really lovely example from your where's it gone? There we go. A really lovely example from your class, because up until this particular point, sorry, I'll get the image up so I'm not talking theoretically. Up until the point where they were asked this, all of the expressions that they'd seen, here we go. There we are. So yeah, there we go, just picking up where we were. Don't know why it won't let me. There we go. So right, what we've got here is, I think I must have said there we go about 12 times. I'll get Sean to edit the video for me there. We've got these two lovely equivalent expressions where 3x, you can see the term in the bars, and then the 18, we can see the area with the ones, or we can think about the dimensions and think of 3 rows x plus 6, which was really great in Chris's class. But when we then moved on to this one, which was very deliberately positioned, because up until that point, the number of rows had always been the coefficient of x. So everything had been 3x plus 12 or 5x plus 10 or 8x plus 24. And this was the first time that the students were asked to make an array with no gaps, no leftovers for something where it wasn't. So you got some really lovely responses for that, Chris, didn't you, with the students?
The class we did it with was a GCSE class, like Sally said, and a lot of them were reluctant to use the tiles. They wanted to use the whiteboards. So there was one lad who, with that one, you know, he had his 10x's drawn out all the way down and then drew half a square, half a 1 on the end. So he factorised it to 10 rows of x plus a half, which led quite nicely into a discussion as, well, technically he's right because he's made his array and it works, it's a rectangle, but mathematically it's not sort of what we would accept, what you would get in sort of exam with it being a GCSE class. And I told him that if he'd used the tiles, he wouldn't be able to rip them, which he replied with, "I would. It's only cards, sir." But you know, we got to that conversation with the point where you can't, if these are fixed, these are 1, you can't cut them in half. So we went back and had a look at why it wouldn't work and how we could make it work.
Yeah, great. And but I thought that 10x, 10 brackets x half just really showed that he understood the structure of what had gone before, and that he was able to use that idea. What you're not allowed to cut them in half, he was able to go, we could do it. 10 brackets x plus half is right. It is equivalent to 10x plus 5. But we have this convention in school algebra where we only want integers, unless you're on where it might be allowed. But at this stage, we want everything to be an integer. So that was a really nice activity to disturb the students and reinforce this idea where you're kind of helping them come into the culture of school maths. I thought that was really nice. So we're looking, we want them ultimately to be able to find the highest common factor and to be able to factorize. And you'll see some other slides when we send them to you where we've got a few other illustrations of this idea, you know, of what is best and how do we know. And then, of course, ultimately, students using this little grid down here, not necessarily having to use the tiles all the time. Because Chris, several of your students were resistant to using the tiles, weren't they? And quite right too. But you were very flexible with whether they drew pictures or not. Yeah,
and I think that grid method you've just shown is very useful when you sort of move into the quadratics. A lot of them, it was a sort of CD borderline class that probably wouldn't have been able to factorize quadratics, but because of the use of the tiles and those diagrams were much more much more willing to have a go at it and more successful at it, I would say, as well.
Definitely, yeah, brilliant. Thanks a lot, Chris. And now there's so much there in the slides that you'll get in terms of ideas. They're not meant to be lessons. We've kind of used these ideas and then constructed them into lessons that match the group that's, or are a good fit for the groups that we've actually taught them. But hopefully there's some ideas, some lesson ideas that we've been able to use where we're starting to build on these ideas of equivalent expressions, and then, which we'll do more of next time, this idea of solving equations when you pin that down and say we want this expression to have a particular value, having gained a deep understanding of what happens when the expression can take all sorts of values, because n or x can be a whole host of different values. So that's something we'll build on in session 3. I've not left much time for questions, but we do have 2 minutes for questions, don't we? If anybody's got any comments at all or any questions, then please fire away. Can I go home now? That's a good question at 5 o'clock on the 13th of January, isn't it? Yeah. Fab. Thanks. So if you think of anything, I think our email addresses are on the PowerPoint and on the first one, which you have from last time or from this time. So please do email any questions or any comments. And like I said, next time we're going to be building on this and thinking about, okay, let's think about pinning this value down now and solving equations with the expression equals expression model. And then perhaps we'll have time to just make some suggestions of how that might link with ideas like sequences or straight line graphs as well. Anything else to add, Chris? Okay, brilliant. Look at that. It's just coming up to 5 o'clock on the nose.
Brilliant. Thank you, Chris and Sally, for another brilliant session. I mean, I think what you're doing actually links very nicely with the new curriculum. You know, what everything I've seen there now is all about conceptual understanding, isn't it? And you know, Chris, what you were saying about those questions, the convince me questions, will develop logical reasoning, wouldn't it, as one of the proficiencies as well. So yeah, thank you everyone for listening, and hopefully, you know, please join us again at the 3rd session. I think it's 3rd of February, another Thursday. So Thursday, 3rd of February at 4 o'clock. And we will share the recording of this session and the PowerPoint with you soon. Thank you, everyone.
Lovely. Thanks a lot, Sean.
Bye.
Thanks, folks.